Right, say you're watching a train go past, right, quite slow, and it's gone 10 metres per second, and someone hoys a brick forward 5 metres per second. Now, using Galileo transforms at these non-relativistic speeds, you can confidently say the brick, according to you, who's not on the train, is going at 15 metres per second. This plus this. Nae bother. However, you're going a bit faster and you cannot use such simple methods of calculating things. Imagine the train now, you're looking at the train, but instead of going 10 metres per second, it's gone 80% the speed of light. Someone's on the top of it and they switch a torch on, and that light comes out the torch at c, the speed of light. You cannot just add these two together now and say the light's going at 1.8 c, or 1.8 times the speed of light. I've put a big cross there saying, no, you cannot do that, because a frizzy-haired bloke called Einstein and his special theory of relativity, he says naught can go faster than the speed of light. So that means nothing can go faster than 1c. And it means whoever's on that train still observes that light coming out the torch to be going at c. But for that to happen, something has to happen with their time, okay? And that's exactly what this video is about. We're going to derive the formula for time dilation. Right, so here is the time for someone on the train. Here's my time looking at the train, but I'm not on the train. And this is gamma. This is what I'm going to call the factor of time dilation, okay? Now check out this little diagram. I've got a source of light S. It's emitting a photon. That photon is travelling at the speed of light c, and c times time will give me the distance travelled, okay? And that's the time in the observer's time frame, the time the observer counts or observes. The source of light is moving to the right at some velocity v, which is not the speed of light, but it's still quite fast. And the source of light will travel his velocity times the time that he observes, which I'm calling time dash. Now me then, because that photon of light was emitted like to the north, I'll see it going in a diagonal direction, and it'll travel a distance, the speed of light, times the time that they observe on the light source, okay? Not my time. So that's time dash. So we end up with this Pythagoras triangle. So we can do a little bit of maths with that triangle and derive the time dilation factor, what I called gamma down here, okay? So using Pythagoras' theory, I've got this side equals the hypotenuse minus the bottom side, right? That's t dash there and t dash there. Now I can distribute the square throughout each term like that, and I can take the common factor t dash out, t dash squared in this case, and have that inside the brackets. Next I can do some algebraic jiggery-pokery, and I can divide both sides by c squared and divide both sides by t dash squared. So that ends up with this situation here, t squared over t dash squared. C squared over 6, that's obviously 1 minus v squared over c squared. V squared's the speed of the train or the light source travelling to the right. C is the speed of light. Okay, I can square root both sides. I end up with the squares disappearing from there and a big square root sign there, and then c's went to 1. Okay, so we're nearly there. The last thing I'm going to do is invert both sides, and it means just flip the fractions over. I get t dash over t equals 1 over the square root of 1 minus v squared over c squared, and that's what I'm going to call gamma, okay? Now, if I make v 0, so the speed of the source of light nothing, all of this gamma comes to 1, alright? So that's if the light source is not moving relative to me, the stationary observer. If I make v, the velocity of the source of light, equal to the speed of light, c over c becomes 1, 1 minus 1 is nothing, 1 divided by nothing is infinity. Alright, so gamma can be anywhere between 1 and infinity. Now what does that mean? What does that mean for our little formula, right? Well, here it means the time for a tick on the clock on the light source that's moving will be anywhere from 1 to infinity. So say it's 2, say gamma's 2. It means a tick on my clock, it'll take twice as long on the clock on the source that's moving. So that means their time, in that case, will be half as fast as mine, okay? And that's pretty amazing. Some pretty amazing consequences. What it means basically is the faster you go relative to me, stationary on Earth, the slower your time goes. It's absolutely mind-boggling, okay? And it's all derived from Pythagoras' theory, alright? It's pretty simple in the end. This is why I love teaching physics, folks.